So let's go over these review problems. This is a review for Chapter 3. Okay, let's go through this. You had to list page 6 and 7 and 9 if this, God bless you, was your classical, your empirical, or your subjective. Now, classical is the same as your theoretical. This has been proven over and over. This is not going to change, and that's how you decide this. Will this change no matter who does this experiment, no matter when I do this? So the probability of randomly selecting 5 cards of the same suit from a standard deck is not going to change whether Heather does it, or Ben does it, or they did it on Thursday, or they did it next year on a Thursday. It will always be the same. We will still do the same probability. So that's your classical, your theoretical. What changes is your empirical. This is the same as your experimental. Remember the E's. The probability of a person from the U.S. being left-handed is 11%. Does the population and the ratios stay the same next year?
No.
No. So that's going to change. That's why this is called empirical. It'll change based on what the makeup of your population is. Maybe all of a sudden we had a larger percent of left-handed people being born. So that's going to change year to year. The probability of rolling a die, any die, is that ever going to change regardless of when we do this?
No.
Nope. So this is your classical. This is your theoretical. Can anybody give me an example of a subjective?
No.
Sure you can. What happened today?
Just 2 hours delayed.
The weather. So, how many places?
Ice, we had Georgia ice.
Right. But what did you hear from the weather last night?
Snow.
Snow. I heard snow. I heard snow starting at 6 o'clock. Then I heard snow starting at 8 o'clock. And now it's 8 o'clock. And everybody below us was getting snow, and we didn't. So when they say the probability of snow is 40%, that's subjective. The weather is a very good indicator for a subjective probability. They see where your weather patterns are, and they also say, well, my gut feeling is that we're going to get 3 to 6 inches. My gut feeling is we're going to get an inch of ice. My gut feeling is this is going to pass us by. That's a little bit of subjectivity into there. That's why you hear the phrase, try to be objective. When someone says be objective when you look at this, objective is the opposite of subjective. Subjective, you put your opinion into it. Objective, you don't have your opinion in it. So when you ask someone's opinion and you say be objective when you look at this, you don't want their opinion to influence it. So subjective says my opinion is in there. Yes.
So will it be safe to say that theoretical and experimental are objective?
Well, not really. We don't really change that, but like you could say like technically because you're experimental, you shouldn't bias it. So you shouldn't have any of your personal feelings into it. But human error does happen. But usually that should be objective as well. Good call on that one. Okay. So number 12. 12 gave us a little chart. And it said for number 12, what is the probability that a randomly selected person in the United States will be less than 60 years old? Now, this is 60 or greater. And this is 85 and over. We want everybody less than 65. We want all of these. So all we do is add them up. This is not mutually exclusive. They are mutually exclusive. These are mutually exclusive. One does not overlap the other category. Another time you might see this is what is the probability that a person is under 85. So 85 and over. You have to add up that. Or you would do 1 minus 100 minus 2%. 98%. This is the complement case. when you do the 1 minus case. And in percentages, 100 minus. Okay? Then you had to decide if this combination of events was independent or dependent. Independent means the probability is not affected by the first thing that happens. Dependent means it is affected. Yes.
Usually it's like you have three pairs of socks in the back. 2 are blue, 1 is yellow. The first time you take blue, and you keep it out. The second time you have different probability because it's dependent because the first one.
Good. Because if you're not replacing, then you have a dependency. It depends what you took and what numbers changed. If you're replacing, you have independent. Your probabilities reset. So tossing a coin 4 times, getting 4 heads, and tossing it a 5th time. Does this have any effect on the one that previously had? No. What's the probability of getting a heads on a coin at any time? 1/2, no matter when you flip it. You may have the luck and flip 10 heads in a row or 10 tails in a row, but it's still independent. Taking a driver's education course and passing the driver's license exam, here's a dependency. And that's a little bit of our subjectivity in here. We say, well, I have a good feeling that if you took this course, you will pass the exam, right? Same thing with this course. I have a good feeling if you take my statistics class, you will pass the final. And you will know all the statistics possible. Okay. And here we have your pairs of socks. Another good way to do this is take a total for white, for black, for blue. So add them up. You have 12 altogether. This is a good way to do this. Make yourself an information box. What is the probability that you select a black and then a blue or white? Put the lines. So first time through, a black, 4 out of 12. Then you have left, you took this one. Go like this. So you took 1 out, your black one, you're not replacing it, you're removing it. And they use the word remove. Remove means not replacing it. So you have a dependent event. So next time around, you have 8 between your white and your blue out of 11. And you want this to happen at the same time. This is your and. Your and says multiply. Right? Good? Okay? Okay, here is another one. This was an or statement. An or says add. But be careful. If they're not mutually exclusive, you have to subtract where they overlap. That's your Venn diagram lesson.
21 asked if it was mutually exclusive or not.
Sorry?
21 asked if it was mutually exclusive or not. They solved.
It did ask?
Yeah.
Yeah, are they mutually exclusive?
No.
No.
Oh.
Do I have the wrong one?
Do it. What?
Right, these are not mutually exclusive.
That's all right.
No. They asked you to find what is the probability that a person selected at random.
I think I'm on question.
I don't know, I think so. This is your at work. This is your at home. This is your overlap.
Job Darian.
Guys, come on, focus on this. This is your boat. This is your boat. This is your Venn diagram. So you have to add your at home plus your at work, and you have to subtract out your boat. That's where they overlap. So you don't want to count them twice. These are not mutually exclusive. Not mutually exclusive. Now, here's a nice one too, and I did this with the deck of cards. I think it's easier to look at. You want the probability of red, go like this, red, and, or means you're adding. Now, here's all my red, these 2 rows. Here's my queens, this column down here. See where they intersected? They intersected at these 2 red queens, which means you counted your 2 red queens here, and you counted them again here. So here's your overlap. you add them and you subtract the 2 that you counted twice. Or could you take this and then just add 2 more? You could do it that way if you're looking at your deck of cards, right? You took this and then 2 more queens I need to count. It works out to be the same answer. Just make sure you worry about where they overlap. And a deck of cards is good to visualize the deck, to see that. These are not mutually exclusive. You have 2 queens that are red. You have to take them out of there. All right, number 27. Number 27 uses your pie chart. And I like the way they use your pie chart. They use your Pareto chart. They use all the charts that we've been talking about. They want to know the probability of randomly selecting a school with 600 or more students. When you have a pie chart, are they mutually exclusive, the parts of your pie? Do they overlap ever? No, so they are mutually exclusive, right? These are mutually exclusive. So you just add the 2 parts together. They're mutually exclusive. Okay, number 30. You're going to use your Pareto chart. And the bars on your Pareto chart cannot overlap. They're mutually exclusive. Just by the fact that it's like a histogram. So find the probability of selecting an adult from the sample who doesn't always eat healthy foods because he or she has no time to cook or is confused about nutrition. Here's your or. Or tells me add. So you're going to find those 2 bars and you're going to add them together. Now because you want a probability, it doesn't stop right there. Probability has to be between 0 and 1. Probability is part over whole. So make sure you give me the probability. Sometimes they say how many people. You just give me this. Probability, you have to put it and make it a probability. That's always one of those things everybody falls into. Okay? 15 cyclists enter a race. How many ways can they finish first, second, third? Write it out. You have 15 to choose from, then 14, then 13. Does order matter when you finish first, second, or third? Yeah, it matters to me if I finish first or third, right? So if order matters, you have permutations. 15 things taken 3 at a time. Can you just do it like this? This is absolutely fine. 5 players on a basketball team must choose a player on the opposing team to defend a one-on-one. How many ways can they choose? Well, if my 5 teammates, my 5 players are lined up, my first player has 5 to choose from. My second player has 4 to choose from, then 3 to choose from, then 2 to choose from, then 1 that's left. So 5 factorial. Gunnar, how would I write this as a permutation?
Do it 24, 34, right?
34. Yeah, but I want to know how should I write this? I did it down, 4, 3, 2, 1.
You do 4, 3, 2, 1, so you do 5 on the left side, right?
Yeah.
And 4 on the other side?
Nope.
You only do 4?
All the way down, 5.
Oh, 5.
Actually, it would turn out to be the same answer as 5 P4, right?
That's what I thought.
It would turn out because the last one is a 1.
Yeah.
But technically, we should have the 5. Okay? All right. Yes, good job, though. What happens here? Okay, 36. An employee must hire 2 people from a list of 13 applicants. Choose how many ways, now they want how many ways that you can hire 2 people. Does it matter what order you hire them in?
Yes.
Well, in this case, no. In this case, no. So therefore, as soon as you say order doesn't matter, combinations. You have 13 to choose from, you want 2 at a time. And here's our old security code ones. 3 letters, followed by 1 digit. The first letter cannot be A, B, or C. That means take them out of your 26. There were no restrictions on your second and third letter. And there's no restriction on your digits. So therefore you multiply these. This is how many ways that you can make that security code. What is the probability that you guess the correct security code? How many ways is this correct? One way. So your probability is 1 out of this. Probability, part over whole. Remember when they ask a probability, your answer has to be between 0 and 1. It can't be this answer. It can't be your final answer. So that would take you a very long time to try to break into somebody's thing that has a security code, right? It would take you a very long time.
Or you can just shoot it.
Okay, here's your defective calculators. Let's see if we can squeeze this in here. Good. You have 200 calculators. 3 are defective. So how many are not defective?
197.
If these are not defective, these are good. Guys, I want it quiet. So, you're going to choose 3 calculators. You're choosing 3. You're picking 3 calculators out of the batch. Does it matter what order you pick those calculators in?
No.
So, combinations.
Yeah.
So, we want the combination that there will be no defective. So, first time through, we need to know how many ways can I pick any 3. Remember, your bottom number is the generic one. Any 3. So start with this first, because this is asking me for a probability, so I need to know that bottom number. Any 3 calculators out of the 200. What is the probability that I get no defective? How many no defectives are there?
197.
197. How many of them do I want?
3.
3. So part over whole. It's a very good chance, if this is a whole room of 200 calculators, that I can choose 3 and have them be not defective, right? I only have 3 in this 200. So it's a very good chance that I pick 3 that are good. Except if you're unlucky and you pick a calculator out of the batch, right? And you pick the one that doesn't have the batteries in it. So find the probability that they're defective. 3 defective. How many to choose from? 3. So this is a very small number. In your calculator, when it does this means move your decimal place 7 positions to the left and fill it with zeros. That's this number. That doesn't mean that your answer is 7.61. It can't be. It can't be a probability. So move that decimal place. The probability that you get at least 1 defective, well, you can get 1 defective, or 2 defective, or 3 defective. What is the only thing that you can't get? No defective.
1 minus.
So there's your complement case. 1 minus your no defective. And this one was the opposite. At least 1 non-defective, 1 non, or 2 non,
3.
or 3 non. The only thing you couldn't get was your defectives. So 1 minus your defectives. And that would be a very strong probability. Questions? Alright, tomorrow's the test, guys.
And we were sort of
They end at the O2.
we're not having that for like.
You still light tonight on the water. Light into tomorrow.
No? Oh, it's supposed to.
Light